Welcome everybody. In this series of videos we will be um, uh, talking about modular arithmetic. So let's start with this definition. So a, b are given integers a, b, n, where n is a positive integer. We say that a is congruent to b modulo n if and only if n divides a minus b. We denote this by writing this notation here. So again, we say that a is congruent to b modulo n if and only if n divides a minus b. So notice that this congruence mod n, this congruence mod n is a relation on the set of integers, because so here this is a relation on the set of integers. So basically a is related to b if n divides a minus b. Here n is called the modulus. Here is an example. 22 and 4, are they congruent modulo n? Well, let's see. What is 22 minus 4? 22 minus 4 is 18, and 18 is divisible by 9, and therefore 22 indeed is congruent to 4 mod n. Is 3 congruent to negative 6 mod n? Well, if we subtract negative 6 from 3, we would be getting 9, and 9 is divisible by 9. So 3 is congruent to negative 6 mod n. Is 200 congruent to 2 mod n? Well, 200 minus 2, that's going to be 198, and 198 is divisible by 9. So we see that 200 is congruent to 2 mod n. Now 13 and 5, are they congruent? Okay, so I have a typo here. Let's, instead of 5 here, let's use 8. So is 13 congruent to 8 mod n? Well, what is 13 minus 8? 13 minus 8 would be 5, and that's not divisible by 9. So 13 is not congruent to 8 mod n. So I have a typo here. Instead of 5, it should be an 8. Here is a set of exercises. So let me skip over another set of exercises. Okay, so let's say, so here I want to characterize all the integers that satisfy the given congruence. So if m is congruent to 0 mod 4, what does that mean? Well, it means that 4 divides m minus 0, which simply means that m is a multiple of 4. So m would be 4 times an integer k. Okay, what if m is congruent to 1 mod 4? Well, if m is congruent to 1 mod 4, then 4 divides m minus 1, which would mean that m minus 1 is a multiple of 4, which would imply that m is 1 plus a multiple of 4. So here k is an integer. So if m is congruent to 1 mod 4, then m is equal to 1 plus a multiple of 4k. What if m is congruent to 2 mod 4? Well, just like in 2, we see that 4 divides m minus 2. As a result, m minus 2 is a multiple of 4, and so m would be 2 plus a multiple of 4. if m is congruent to 3 mod 4, then m would be 3 plus a multiple of 4. If m is congruent to 4 mod 4, then we know that 4 divides m minus 4, or m minus 4 is a multiple of 4. But then if you solve for m in this equation, you're going to get m is equal to 4k plus 4, and then 4k plus 4 is just a multiple of 4. So we see that then m would be a multiple of 4. So again, if you put the negative 4 on the right hand side, you see that m is a multiple of 4. So m is congruent to 0 mod 4. So if m is congruent to 4 mod 4, then m is in fact congruent to 0 mod 4. Okay, so notice that negative 3 is congruent to 1 mod 4, because negative 3 minus 1 would be negative 4, and that's divisible by 4. Now, if m is congruent to negative 3, then I want to show that m is congruent to 1. So if m is congruent to negative 3, then m would be negative 3 plus a multiple of 4. So if m is congruent to negative 3 mod 4, then m has to be negative 3 plus a multiple of 4. So, but negative 3 is congruent to 1 mod 4, so then we see that this is equal to, okay, sorry, so negative 3 plus 4k. Okay, I'm going to rewrite that as, I'm going to put a 1 here, and then 4k remains the same, and in order to make sure I still have negative 3, I'm writing negative 4 here. So I have negative 3 plus 4k is equal to 1 plus 4k minus 4. And so 4k minus 4 is just a multiple of 4. So let's write 4k prime. And so we see that then this means that this quantity is congruent to 1 mod 4. So we see that if m is congruent to negative 3 mod 4, then m must be congruent to 1 mod 4. So if negative 3 is congruent to 1 mod 4, then, and if m is congruent to negative 3, then m must be congruent to 1 mod 4. If 5 is congruent to 1 mod 4, then we see that m, okay, so if 5 is congruent to 1 mod 4, and if m is congruent to 5 mod 4, then m must be congruent to 1 mod 4. If 6 is congruent to 2 mod 4, well, 6 is congruent to 2 mod 4, and we get that if m is congruent to 6 mod 4, then m must be congruent to 2 mod 4. Okay, so I hope that this exercise helps in thinking about this congruences. Here's a set of exercises which is similar to the one that we just did. Okay, so now remember the definition of the congruence. We said that we are defining a relation on the set of integers. We are saying that a is related to b, or a is congruent to b mod n if and only if a minus b is divisible by n. N is called the modulus here. So the question is this relation an equivalence relation? And let's answer that. So the answer is yes. So for any a and a positive, so okay, so let's let n to be a positive integer. A, b, and c be integers. I forgot to write b and c here. So the first statement is a is congruent to a mod n for all n, for all integers a, and the reason is clear. That is, a minus a, which is 0, is always divisible by n. So we say that a must be congruent to a mod n. Now, if a is congruent to b mod n and b is then b must be congruent to a mod n. So this is the symmetric property. Well, this is also pretty clear because a is congruent to b mod n means that a minus b is divisible by n. But if a minus b is divisible by n, then the negative of that, b minus a, is also divisible by n. But this exactly means that b is congruent to a mod n. So the congruence relation is an is a symmetric relation. And lastly, let's check the transitive property. If a is congruent to b mod n, and if b is congruent to c mod n, then a must be congruent to c mod n. Why is that the case? Well, if a is congruent to b mod n, it means that a minus b is divisible by n. B is congruent to c mod n, it means that b minus c is divisible by n. Well then, since a minus b and b minus a are divisible by n, if I add a minus b and b minus c, the sum will be divisible by n. So since n divides each summand here, n must divide the sum. So this is a vertical sign here, and I forgot to close the bracket here. So, but a minus b plus b minus c is exactly a minus c, so you see that n must divide a minus c. So we see that our congruence relation is reflexive, symmetric, and transitive. As a result, it is an equivalence relation. Let's let a, b, c, d be integers and n be a positive integer. If a is congruent to b mod n and c is congruent to d mod n, then we can say, number one, that a plus c is, if a plus c is congruent to b plus d, that is, if I add the left hand sides and the right hand sides, then the sum of the left hand sides is congruent to the sum of the right hand sides. I can say the same thing when I subtract. So a minus c is congruent to b minus d mod n. And I can also say that ac is congruent to bd mod n. So here I'm multiplying the left hand sides. This is the product of the right hand sides of these two congruences. So I'm not going to prove number 1 and 2. I'll leave that for you to go over yourself. Number 3 is what I'm going to verify now. Well, the fact that a is congruent to b mod n, that simply means that a is equal to b plus a multiple of n. Similarly, the fact that c is congruent to d mod n, it simply means that c is equal to d plus a multiple of n. So now I'm in these two equations, we're going to multiply ac here. So a times c would be the product of these two right hand sides. So ac would be b plus nk1 times d plus nk2. And if we multiply out here, notice that I'm going to get bd here. And then all the other terms will be a multiple of n. So when I multiply b with nk2, that's a multiple of n. d nk1, that's a multiple of n. And nk1, nk2, that's also a multiple of n. So when we multiply out here, we're going to get four terms. One of them is bd, and the other three terms would be a multiple of n. So the other three terms will just be a multiple of n. So we see that ac is equal to bd plus a multiple of n. So clearly then ac is okay, so I have a typo here. What I wanted to write here is AC is congruent to BD modulo n. All right, so this is here we have a set of exercises here. Let me make a comment about the second exercise here. So here we have that AC is congruent to BC mod n. Then can we say that A and B are congruent to each other mod n? So recall that when we have an equation, usual equation, we can cancel out the C and say that A and B are equal when C is not 0. But can we do the same? That is, can we cancel C and say that if this congruence holds, then then we can cancel C and get A is congruent to B mod n. Okay, so I want you to think about this in the context of n. So think about when n is a prime number and when n is not a prime number, and see if this statement if this congruence implies this one. Okay, so now a very important statement theorem that if A is congruent to B mod n if and only if A and B have the same remainder when divided by n. So if we divide A and B by n, we then get the same remainder. Here's how we're going to check. If we apply the division algorithm, that is, we can divide A by n, and then we're going to get a quotient and a remainder. Similarly, if we divide, okay, I have a typo here, this should be a B. So if we divide B by n, then we get a quotient QB and the remainder RB, and RA, RB will be strictly less than n, and they will be non-negative. Okay, so then if you look at A minus B, so remember this is B, I have a typo here. So A minus B would be this minus this, and this minus this would be n times QA minus QB plus RA minus RB. Okay, so that's going to be A minus B. Now, if RA and RB are equal, so that is, I'm assuming this statement here. So if A and B, they have the same remainder when divided by n, that is, if RA and RB are equal, then, well, this would be 0, and if this is 0, then we see that A minus B is a multiple of n, so then it's divisible by n, and so A is congruent to B mod n. So if A and B, they have the same remainder when they are divided by n, then A and B are congruent to each other modulo n. On the other hand, if A is congruent to B mod n, so I'm assuming that A is congruent to B mod n, well then n divides, so then n will divide A minus B, but if n divides A minus B, then n will divide this quantity, but okay, let me say it again. If A is congruent to B mod n, then n divides A minus B. But if n divides A minus B, n already divides this because it's a multiple of n. So n divides this guy, n divides this. So therefore, n must divide this quantity here. But remember, RA, RB, both of them are strictly less than n and non-negative. So RA minus RB would be smaller than n in absolute value. So therefore, the only way n divides that is when this is 0. So then I can say that RA is equal to RB. Okay, so that completes the proof of this theorem. We have seen this example before. So so what this is telling us is the following: if the modulus is 4, then every integer is congruent modulo 4 to one of the integers 0, 1, 2, and 3, which are called residues modulo n. So basically, when you divide any given integer, when you divide it by 4, you would get a remainder of 0, 1, 2, or 3. So by the previous theorem, then any integer would be congruent to one of these 4 numbers modulo 4. and you can see that in the first line here I have all the numbers that are congruent to 0 mod 4. These are all the numbers that are congruent to 1 mod 4. These are all the numbers that are congruent to 2 mod 4, and these are all the numbers that are congruent to 3 mod 4. So notice that as you go down, you're just adding 1 to the previous line. And if you look at it, this covers all the integers here are covered. So these are actually so remember, congruency is an equivalence relation. This one is the class containing 0. This one is the class containing 1, class containing 2, and class containing 3. So these are the distinct classes modulo 4. Any other class would be equal to one of them. So the class of 5, for example, a class of 4 would be the same as the class of 0. Class of 5 would be the same as class of 1, and so on. Okay, so here we just said that A is congruent to B if and only if A and B have the same remainder when they are divided by n. So if m is a positive integer, given an integer a, by division algorithm, we have that a is equal to bm plus r, where r is between 0 and m minus 1. So we are dividing a by m. So clearly then we see that a minus r is a multiple of m. So then we see that a is congruent to r mod m, because a minus r would be a multiple of m. So a is congruent to r mod m. So what we have is that any given integer a, when we are fixing m here, fixing an m, any given integer a is congruent to r mod m, where r is the remainder obtained when a is divided by m. So every integer is congruent modulo m to the remainder when it is divided by m. So then every integer is congruent modulo m to one of the numbers 0 up to m minus 1, because these are the only possible remainders when we divide by m. Since notice that no two of these integers are congruent mod n, because they are all strictly less than m, and if you take their difference, it will still be strictly less than m, and in absolute value, as a result, no two of these numbers will be congruent. So we see that we have m integers such that every integer is congruent mod m to exactly one of the m integers. So every integer is congruent to exactly one of these numbers modulo m. Given a positive integer m, a complete set of residues modulo m is a set of integers such that every integer is congruent mod m to exactly one integer of the set. So what am I saying here? If you look at the set 0, 1 up to m minus 1, that's a complete set of residues modulo m, because these are no two of them are congruent to each other, and so they are pairwise incongruent, and any integer is congruent to one of them modulo m. Here is another set of another complete set of residues mod m. So if you go from 2 up to m, I'm missing a comma here after m. So if I look at all the integers from 2 all the way up to m plus 1, then that's also a complete set of residues modulo m, because notice that m is taking the place of 0, m plus 1 is taking the place of 1. So this is also a complete set of residues modulo m. Notice that if I take any set of m consecutive numbers, that's going to form a complete set of residues modulo m. The set of integers 0, 1, 2, and 3 is a complete set of residues modulo 4. Another way of thinking about this is that they represent distinct classes for the relation congruence modulo 4. 2, 3, 4, 5, that's also a complete set of residues mod m. Notice here, sorry, mod 4 here. This is a typo. This should be a mod 4 here. So notice that mod 4 is 0, and mod 4, 5 is 1. Given a positive integer n, the set 0, 1 up to n minus 1 is called the canonical complete residue system modulo n. Okay, so I will stop here, and we will be talking more about modular arithmetic in the next video.